So in this video I want to talk about low energy nuclear reactions and its applications for the synthetic production of platinoid metals. So in this case we're looking at transmutating tungsten into platinum. Now for those that are not familiar with low energy nuclear reactions, you can look at a lot of the literature from the cold fusion community, the LENR community, and what these guys have done over the past 30 years now is basically replicate the work of Fleischmann and Pons, which at the time was, they did discover something that's scientifically and physically valid, that has been replicated, has been reproduced. It has been ignored by the mainstream scientific community, mainly because it really puts into question a lot of conventional nuclear physics. It seeks to it's a very anomalous finding, and it poses problems for the mainstream physics community. So they've really attempted to suppression might sound conspiratorial, but it really has been almost a suppression because the hot fusion guys, what you can call big fusion, right? They get all the funding from the government. So the low energy guys have really never been able to get any government funding, even though they have been able to replicate their findings. And so where I differ is that I look at low energy nuclear reactions the way that Mitsubishi does, and that is it could be useful for transmutating radioactive waste, so nuclear waste, where you would transform the radioactive isotopes into, well, not longer lived non-radioactive isotopes, and perhaps even producing synthetic elements. And so for many people this sounds physically impossible or bordering on the realm of pseudoscience, but if you look at the literature, which there's an ample literature, you find that not only is it physically possible, but it could also be economically possible, in the sense of the amount of deuterium that would be needed is actually very minimal. So in the case of transmutating tungsten into platinum, you're going to use 8 neutrons. So you go from tungsten 182 to platinum 190, and you're going to add 4 protons. And so deuterium gas costs something. Well, deuterium gas uses about 200 to 1,000 kilowatt hours per kilogram of heavy water. And so when you electrolyze the heavy water, 12%, well, 14, in that case, 24% would be deuterium. Water is about 11.8% hydrogen, so deuterium has twice the mass. So you're looking at a pretty significant energy expenditure for producing the deuterium. But the interesting thing is that the actual the change in mass is very minimal, right? You're going from something that weighs something that's 74 protons to 78 protons. That's not a big increase in mass. So the actual quantity of deuterium gas needed to perform this reaction is quite minimal. So then the question comes in: how much deuterium, how much platinum could you actually produce? And that really depends on the kinetics of the reaction, how what kind of reaction intensity you can achieve, because most of these transmutation reactions under low energy conditions, they produce very minimal products, and so you find that you might get a few nanograms of material. So in the case of this research here, this from Mitsubishi, and they had originally done this in I think about 2001, and they used a palladium lattice, and they doped that with cesium, and then they got strontium 90, they got praseodymium, and another metal, I think cobalt. But again, they actually had to use neutron activated analysis, because the mass spectrometers couldn't even read the concentration of the nuclear waste products, which was those 3 metals that I listed. So you're obviously, these reactions are very low intensity reactions, so the rate at which these reactions take place are very slow. And so in order to do this commercially, you would have to obviously really process intensify this. And so you probably have to increase the pressure of the deuterium gas, which has been studied. Higher pressure does increase the conversion rate. And one of the other objectives would be of course, replace palladium, because palladium is an expensive precious metal, perhaps replacing the palladium and using titanium instead, or nickel, which has been found to sustain low energy nuclear reactions. So the reason we're talking about transmutation and not just heat production is because the heat production results are not as promising, and the reason for that, the main reason for that, is that the actual heat, the excess heat produced, is quite minimal. Most reactions have produced excess heat around 1.10, ratio about 1.10, so you get 10% extra heat. Mizuno has been able to produce around 2 times excess heat, but you're talking low-grade heat. This is pretty low-grade heat, and so you'd have to use maybe a Stirling engine or thermoelectric generator that has pretty low efficiency, and so the actual net heat output would be quite small. And of course, you have to take into account the energy needed to produce the deuterium. So heat production or power production from low energy nuclear reactions may not be what first brings about a commercial application. Mitsubishi is not really looking at this for energy production. They're looking at it to as I mentioned, dispose of radioactive nuclear waste. So they understand that the actual heat production, if you can look at all the data on excess heat production, but it's not nearly as promising as some people have claimed. So I think the most interesting application would be the production of and so here you can see the reaction pathways. So you have this was the first reaction, so that was cesium into praseodymium, and then you have strontium into molybdenum, barium into samarium, and calcium into titanium, tungsten into osmium, and then tungsten into platinum. So a lot of different reactions that can be sustained. And of course, the most interesting is one from a more abundant element into a less abundant element. In the case of tungsten, you have about 3.5 million tons of tungsten reserves. We only have about 50,000 tons of platinum. So you're taking a commodity that's worth, or in the case of tungsten, sells for about $100 per kilo, and platinum sells for $50,000 a kilo, right? And so the cost effectiveness of that conversion process is quite substantial, considering the fact that we could basically take an element that doesn't have as many commercial uses or industrial engineering applications. Tungsten isn't really that useful. I mean, platinum has tremendous engineering applications, from fuel cells, catalytic converters, to electronics, etc. So if you can turn tungsten into platinum, that's perhaps $1 billion, or if not $1 trillion industry, if this can be scaled to commercial levels, and the kinetics and the process intensification of these low energy nuclear reactions can be achieved. So here you can see the pressure versus conversion rate, and so that's for cesium into praseodymium, and you can see at higher pressures you're getting a higher conversion rate. So they're getting about 70% conversion at 230 kilopascal, and so it is possible to again process intensify this reaction, and if you can do this, if you're thinking about the economics of this reaction, if you're using a palladium lattice to achieve this reaction, what you have to find is, and I don't have this number, is actually the power density. So how much material you're going to be able to produce, let's say, per kilogram of palladium. Assuming the hypothetical 1 kilogram of platinum produced per year, that's on 1100 micrograms per hour. Now, we don't actually know how much palladium lattice we're going to need in order to actually produce 1100 micrograms per hour, because we don't know the actual process intensity of this reaction. We don't know actually how many deuterons per second are fusing into the doped tungsten, because that's one thing that is going to have to be developed as an efficient method to actually deposit small amounts of tungsten on the surface of the palladium, and how do we go about regenerating that? Do we have in situ regeneration? Do we pull out the palladium lattice every once in a while and regenerate it? These are unknowns. We still have to develop that, but the actual kinetics, if we know it's physically possible to turn tungsten into palladium, then we just have to figure out the fine details. So the most important problem has been solved. some people might be kind of skeptical and they say, well, you should focus on energy production. But the problem with energy production, as I said, is the excess heat. Even if the excess heat is sufficient at a gross level, right, you might get, let's say, 80% excess heat. But if the heat is low grade, then the Carnot theorem would force you to have poor conversion efficiencies. So that's my only concern. I think is the actual, say, watt per deuteron used is going to, so as I said, deuterium heavy water at the low end, they say about 200 kilowatt per kilogram. So if you take 200 and divide that by let's say 22%. So I think water is 11% hydrogen. So we have 22%. So we take 200 divided by 22%. That's 900 kilowatt hours per kilogram of deuterium. So it's a very significant amount of energy. Now we would likely get far more energy out because the conventional fusion, right, is what, 8 million megajoules per kilogram or something, right? But in this case, they estimate far less than that for these low energy nuclear reactions. You're probably looking at, the estimate has been, if you take 8 million for regular fusion, divide that by 40, that's 200,000 times chemical fuels. NASA estimated that for LENR, you're looking at more 4,000 times chemical fuels, right? Take 40 megajoules times 4,000, maybe 160,000 megajoules. So yeah, you're still getting, a lot more, but if you take that times 0.27, that's 43,000, right? You're using 1,000 to produce the deuterium. So, it's you're going to have a positive ROI for sure, but we don't really know exactly how we're going to convert this low-grade heat, and especially at these ratios, because if you look at Biberon's book, I can bring that book up right now, actually, if I have enough. As illustrated in this chart, you can see that as higher deuterium pressures, the excess heat ratio goes up, but it's still only 1.4. And that's an issue, because the conversion efficiency of excess heat is somewhere in the order of probably less than 20% for a small-scale reactor. And considering the temperatures are 200 C is not considered excess low-grade heat. I mean, definitely with a organic Rankine cycle using the using an organic Rankine cycle, you probably achieve efficiency of around 20% for a small-scale steam turbine. So if we take if we assume we're at the high end, if we have an excess heat ratio of 1.4, so let's say we have 100 watts going in, we have 40 watts coming out. If we take 40 divided by, let's say, 20%, that's only 8 watts left. So this is sort of my argument about the viability of energy production with condensed matter nuclear fusion. I think what's more interesting is, as these guys said, like sort of more perhaps slightly less sexy and a bit more mundane applications, like disposing of nuclear waste, or what I think is more interesting, producing platinum, because I think fuel cells are the future of low emission transportation, and in order to scale PEM fuel cell technology, we need large amounts of platinum. And if people are not willing to mine the seafloor for platinum, which by itself might not even be economically viable, we're going to need sources of platinum. And so I ironically actually stumbled upon this because I was researching I stumbled upon low energy fusion reactions because I was studying Edwin Cull's model of the structured atom theory, right, which is this sort of controversial theory that the nucleus doesn't have neutrons. There's no strong nuclear force, and that you actually just have protons and electrons, and that is somewhat more congruent with these findings of low energy nuclear reactions, because a lot of, like Huizinga said, where are the neutrons coming, and the answer is where I should say where the neutrons, they're not present, and so it's anomalous, and I think that's why the structured atom model might make sense. But anyway, that's a whole different story. I think the these results here, you can see, okay, so for this, like, it's different iterations, different reactor models. So Their input-output ratio is, at the low end about 1.12 and the high end like 1.4. And again, this is still pretty awesome because if you think about it, the gross heat output is, the power density is nearly a watt per gram. That's very high power density. So if one could develop a thermoelectric generator that's more efficient, I think that's going to be difficult because thermoelectric generators peak out at about 7%. So we probably would want to use an organic Rankine cycle with a suitable working fluid, R134 or whatever they use, and in fact I can just quickly search organic Rankine cycle, typing with one hand because I'm holding my mic, as you probably know. Fluids, yeah. So I think R134 is a common fluid. Back a few years ago I was studying ORC technology. Let's even see if R134 exists. Yeah, R134A. Pretty sure that's what you'd want to use. Yeah, so it works between 35C and 75C. System efficiency of 7 and 4%. That's the issue, is that low efficiency. If we can try to get 20%, that would be nice. They find definitely under 20% is a typical number, but the efficiency of current high temperature ORC does not exceed 24%. That's my only sort of apprehension about this technology is the fact that even if the net heat output is sufficient, like 1.4 is a healthy number. If you take 40 watts and multiply that by 20%, you're not getting a whole lot left. And so you're going to need, and the other thing is, how do you scale this technology? You need palladium. If we want to produce gigawatts of energy, we'd have to mine all the palladium. So again, it's not a panacea. Cold fusion is not a panacea. It's technically viable, unlike these people that discard it as pseudoscience. It is technically valid. In fact, even mainstream people are coming around to admitting there's something to it. I think the current effort to use it for energy production is probably misguided. So regarding the actual isotopes of platinum produced, as we can see from this chart, that the main isotope produced was 195, not 190, and more likely the 190 was actually osmium. So the actual number of neutrons needed, if we're taking platinum 195 from tungsten, let's say 185, then obviously we need 10 neutrons, and that's going to come from our deuterium. So we're going to need exactly 10 deuteriums. As for where the protons go, well, we're not going to need as many protons, so we're going to be left over. We're going to be left with leftover protons. As for where they go, I'm not quite sure. So again, I think the most important question here is how do we go about doping the tungsten onto the palladium? How much palladium do we actually need? And what's our production rate? Those are unknowns, but we're starting from the bottom, which is the physics and kinetics, and then we're moving up into the more micro level details.